Thank you very much, everybody, for coming today. My name is Dougal Ballantyne. I'm a solutions architect with Amazon Web Services. I work in our high-performance computing group. That means we focus on, customers are trying to build really cool, interesting projects that have a lot of high-performance compute needs, storage needs, and network needs. EBS is one of my favorite products. I spend a lot of time playing with EBS, trying to get the most performance out of it for our customers. And so it's my pleasure today to do the EBS deep dive. We're going to be covering an overview of EBS. We're going to go into all of the components of EBS and how they relate to you as customers using them. We're going to cover volumes, snapshots, best practices around volumes and snapshots. We'll talk about encryption, one of the great capabilities of EBS, and then we'll make time for Q&A. We'll hopefully try and make time for 5 to 10 minutes of Q&A at the end. So let's start with the overview of EBS. For most builders, AWS is get in and go, and that applies to EBS as well. You can typically just launch an instance, attach an EBS volume, maybe 20 gigabytes, 50 gigabytes, store your data on that volume, and you'll never need to worry about what you're doing with it. You'll typically get the most performance out of it due to things like general purpose volumes where we have burst capability, and you don't need to worry about any other settings around, queue depth or the capabilities of the volume itself. But there are times where you need to know more about EBS. It helps when you're building something, when you're truly architecting a solution on top of AWS, that you understand some of the reasons you might choose one volume type over another, or understanding how to make sure snapshots are the right components you're using, or how to make sure snapshots are being taken in the correct way, so you get the most out of the service. So a normal hard drive. I sadly have committed most of these things to memory over the years because I used to build storage arrays, and you need to work out the rotational speed or the throughput of volumes or the IOPS of a volume. If you get it wrong, a RAID 5 array is very poor performing, and next thing you know, you have people asking you why their application doesn't perform. Fortunately, the EBS team knows an awful lot about hard drives. In fact, they take away all of the undifferentiated heavy lifting of picking out the hardware and making sure the hardware is looked after. And they expose that as a service, something you can then consume with some very simple parameters to make it possible to have some different configurations on top of your systems. That being said, it's very important to understand EBS is not just hard drives. EBS is a service. It's fundamentally more than just a drive attached to your EC2 instance. So it's network block storage as a service. And I'm going to reiterate this several times, as a service. This enables us to do things with EBS you just can't do with a block device attached to a server or attached to your instance. Designed for 5 nines of availability, so it's designed to be available a lot of the time. That's a really high availability number. EBS volumes attach directly to EC2 instances in the same availability zone. So when you launch an instance into, let's say, for example, US East 1A, you would create an EBS volume in the same availability zone, or AZ, and then you can attach it to the same instance that you just launched. And it also has the capability to do snapshots, a point-in-time copy, and also incremental copies thereafter of your data, which is stored in S3. And that data, once it's stored in S3, gets the same durability benefits that S3 provides to the customers, so 11 nines of durability. And then you can do things with the snapshots like create new volumes in another availability zone, or even copy volumes across to another region, or share the snapshot with another account if you want to move data between one account and another account. A little bit more about EBS. Just to reiterate, it's a service. It's not EC2. It's independent of EC2. It's a service that you attach to an EC2 instance. It operates inside the EC2 world, if you will. But it's not EC2. It's a service team on its own, and their goals are set for the EBS service. So when we talk about goals, it has regional and AZ availability goals. All EBS volumes, and that means all the volume types, magnetic and SSD based, are designed for 5 nines of availability. And just to give some numbers around the scale of the platform today, there's over 2 million volumes created per day. And that's a staggering amount of volume creates. And when you realize what you can do with that, you can just create a 1 terabyte volume or a 16 terabyte volume and within a couple of seconds have it attached, it's pretty phenomenal. So a few definitions before we get too far into the presentation. I think it's important that if we set some definitions, everyone knows we're talking about the same thing for the EBS service. So IOPS, input and output operations per second, it's typically a number, and this is more associated with things like provisioned IOPS, where you might choose to have a number of provisioned IOPS for your volume, 8,000 for example. Throughput, the read and write rate to storage. And this is something that's typically discussed when we talk about what a volume is capable of providing. So for example, 320 megabytes a second for a provisioned IOPS volume, or what the instance is capable of achieving. Instances have different capabilities. Latency, the amount of time it takes for a request to be completed. And this is important to understand. We share these metrics with you in CloudWatch so you can take a look at the performance of your storage system and make decisions around whether you're using it effectively or if you've got the volumes appropriately sized. Capacity, pretty easy one, the volume of data that's stored in gigabytes. And we announced last year and launched since the last time we did the EBS talk, you can now do up to 16 terabytes in one volume. So it's very easy to create a large amount of storage and quickly attach it to an EC2 instance. And then the block size, and the size of I/O that you're sending to the device, or the size of I/O that's being measured by EBS. Now, EBS measures IOPS. That's the primary measure it uses when it's looking at the performance of the volume. And those IOPS are typically measured in 256 kilobytes. And we actually do something called I/O merging to make it possible for you to get more I/Os even if you're not doing 256. And there's a future talk, talk right after this, so if folks are interested in going even deeper in EBS, where we'll do performance on EBS at an even lower level. So before we get into the actual volumes, how the volume types operate, the different types of volumes that are available, I think it's important to take a moment to talk about volume management. Now, because volumes are resources, like everything else in AWS, it's actually worth taking a moment to think about, how am I going to manage my volumes? What will I do with the volumes as I'm creating them? So the first thing is tagging. So for folks who are not tagging instances or not tagging volumes today, this is my first ask of you, if you will. Please tag. You should tag everything. You could do today, I think, 10 tags, and that doesn't count the ones that are automatically added if they've been created by CloudFormation or they've been created by autoscaling. Add tags everywhere. Tags enable you to then very easily find, sort, keep track of the purpose of a volume, why it was created, possibly what application stack it's associated with. Is it production data or is it dev test data? Or is it a scratch volume? And so it's very important to tag volumes. That will enable you in the future to go through. The worst thing you can have in your EC2 console, from my perspective, is a whole bunch of unattached volumes. They just sit there with a little blue icon, and you're not sure what they are. And the really hard thing is the only way to work out what they are is to go and find an EC2 instance, attach the volume, look at the volume, and you're like, oh, scratch data, delete volume. And that's kind of a lengthy process if you have a lot of volumes. The delete on termination flag. So this is a rather interesting thing that I wanted to highlight, so try and catch out customers who don't realize this. Typically, when you have an EC2 instance and you have an EBS-backed instance, so it's using an EBS root volume, the delete on terminate flag is set to yes for that volume. That means that when the instance is deleted, the volume is automatically deleted. So a relationship between the two, so that when something changes, that we keep track of it for you. If you've got a data volume attached to that EC2 instance, so you've added an extra volume maybe for some more data, and you don't have the delete on terminate on that, and maybe you have it in an auto-scaling group where you're launching a lot of these instances, those volumes will stay there when the instance is terminated. You'll very quickly discover you've maybe got 20, 30 or more volumes sitting there unattached to instances. And it's persistent storage, so it stays there. It's designed to stay there. Like, we built it so that when you want it to stay there, it stays. So it will stay around unless you look after it. So we go back to volume management. Please do that. And you should really have an approach on this. So I mentioned scratch volumes. Tag things that you know in the future what you want to do with a volume. So volume initialization. What happens, or what is the state of a volume once you create it? So in previous years, I would talk about pre-warming at some point in the presentation. What I want to talk about now is the fact that we don't recommend pre-warming for our volumes. There's been a lot of work done in the service, and that's the important thing. It's a service, so you don't notice these things until we tell you. But you now create a volume, and you should just be able to use that volume straight away. That volume is ready to go. Volumes are stored from snapshots. There's a lazy load of data from S3. So in some cases, although I will say it's quite rare, you may want to read ahead on the volume to get that data in a little bit quicker. But it's typically not recommended either, because you're going to spend time reading into a volume that you don't really need to read into. So the different volume types. Today we have 3 volume types on EBS. We have magnetic volumes, which are the original volumes when the service launched. We have General Purpose SSD, which we consider our default volume type, and I'll talk a little bit around why we consider our default and why you should hopefully be using it as well. And then we have provisioned IOPS, which is the volume type focused and enabling you to give a very precise definition of performance you expect from the volume. You can dial in the IOPS and the size for things like tier 1 databases or mission critical applications you want to run on top of the system. So let's start with the general purpose SSD volumes. So general purpose SSD, I think, is a really unique piece of technology that if you've spent time working on storage subsystems, if you've actually had to rack and stack arrays, this is really cool. It's a volume that has a baseline performance, so you know what the volume will deliver, along with the capability to burst substantially higher on smaller volume sizes. So this means you don't need to over-provision your storage capacity to get the performance you're looking for, because it's rare that someone has an application that runs 24/7 flat out. If it does, then there's probably a different volume type you want to configure. And here you get access to a significant amount of IOPS and throughput when the volume is still quite small. So every GP2 volume starts out with 100 IOPS baseline. And I'm going to talk about something called the credit bucket and how the burst works in a little bit more detail. And you get 3 IOPS per gigabyte. So you should be able to provision up to 10,000 IOPS on 700 gigabytes, if memory serves me correct. Throughput is up to 160 megabytes a second. And we'll talk about that a little bit around the fact that throughput and IOPS, although related, are 2 different properties of the volume. Latency is designed for single-digit millisecond latency. And it has a performance target of 99%. So that's performance of IOPS. So 99% of the time we're striving to provide all of the IOPS. And we consider it the volume that most workloads will default to on AWS. So a little bit to understand how the burst and baseline works. So when we launched the GP2 volumes, they were up to 1 terabyte in size, and up to 1 terabyte would give you 1,000 IOPS. Sorry, 3,000 IOPS. And once you'd created that volume, that was as large as it would go. When we launched 16 terabytes, it's now possible to have a volume larger than our burst bucket was providing. And so what we're trying to do here is illustrate, and some of the EBS engineers always get annoyed because the graph is not to scale. But what we're trying to illustrate here is the fact that as you increase your volume size from 0 to 1, that increases the size of baseline IOPS, or increases the amount of baseline IOPS you have available. But you still have access to the yellow area, which is the burst IOPS. So you're always going to be able to burst up to 3,000 IOPS. And you're going to be accumulating at your baseline IOPS. If you go above 1 terabyte in size, the baseline performance of the volume exceeds the burst capability, so that is the performance of the volume. So if you were to create, for example, a 3 terabyte volume, you would get 10,000 IOPS. There is no burst at that point because you've already exceeded what the burst capability would be. So let me try and take a moment to explain how the GP2 bursting works. I think it's really cool. I will say that it's a little hard to understand the first time, but once you understand it, you'll realize it's a very powerful capability that will enable you to size volumes for the data you're storing rather than trying to achieve a certain level of IOPS. So the first thing is every single volume created in GP2 is given a burst bucket allocation of 5.4 million IOPS. And once you've got that burst bucket, you start accumulating because the volume's been initialized or created. So if we had a volume that was 100 gigabytes, we'd be accumulating at 300 IOPS every second as well. And then you can spend at whatever your baseline, up to 3,000 or higher if on your baseline, IOPS out of that volume. So in this example, we use, say, 1 terabyte for the size. We can spend at 3,000 IOPS out of that volume. And it'll still be accumulating as it comes in. Now, a lot of people associate the term burst with something that is very quick, very instantaneous, a firework going off or something like that. It's actually not the case with GP2. So we have a very, very low percentage of volumes that are actually exceeding or emptying their burst bucket. And in general, when that happens, it's typically people who are testing for that scenario. They're testing to see how long it takes for them to empty the GP2 burst bucket, rather than actually production use of the volume. And just to highlight this, this is a graph of the size of a general purpose volume, GP2, and the time it would take to fully empty the I/O burst bucket if you were running at 3,000 IOPS all of the time, so flat out. And that's actually pretty hard to do. That's a lot of IOPS to be running through a volume. And just to give you an example, I'll highlight one here. So if you had a 500 gigabyte volume, It would take you 60 minutes, so a full hour, of flat out, not once dropping below 3,000 IOPS, to actually empty the burst bucket in that volume. And the reality is, when you take a look at how systems actually operate in practice, there's no way it runs flat out for 60 minutes. It's going to drop down a couple of times, and when it drops down, it's accumulating more than it's using, so that burst bucket's not emptying. So a little bit of an example of how general purpose volumes work, or at least what the difference they're making for different workloads and applications. So if I take an example of a Windows boot volume, they're typically about 30 gigabytes in size. So the burst bucket is automatically 5.4 million IOPS at the beginning. It's going to get a baseline performance of 100 IOPS, because as we said, there's a 100 IOPS floor on the volumes, but it will be accumulating at 90 IOPS per second because it's a 30 gigabyte volume, 3 IOPS per gigabyte. This volume could burst for 30 minutes at 3,000 IOPS. Now, Windows typically boots a little bit slower than Linux, but it definitely doesn't take 30 minutes to boot a volume. And so what this means is the boot time on Windows is substantially accelerated. And so we did some testing to try and highlight this, and there's two specific OSs I wanted to highlight. So the first one is Windows. So if we take a magnetic volume for the boot volume, we're typically seeing an access time, so that's the time where you can get in and start using that instance, of 7 minutes and 16 seconds. When we move the volume to GP2, and when I say move the volume to GP2, that means literally if you're in the console choosing GP2, you don't need to do anything else. If you're working in an auto-scaling group, updating the block device mapping so that it picks up GP2, you don't need to change anything fundamental in your application. Nothing in Windows is changed to make this happen. It's almost 40% quicker to boot that Windows instance. The second one I want to highlight is the fact it does also help speed up a Linux instance. The reason I call out CentOS specifically here is the CentOS 6 in the marketplace actually defaults to magnetic. So if you're launching CentOS from the marketplace and you're not changing the boot device as it launches in an auto-scaling group or from the console if it hasn't popped up to tell you, then you're actually booting onto magnetic rather than GP2. And you can see it also makes a substantial speed up in boot time for the Linux instance. A second example I want to give is going to highlight the fact that you can achieve substantial performance from a GP2 volume. In fact, similar, if not more, from a burst perspective than you would with provisioned IOPS. However, it's a much lower cost in the environment. Now, if in the past you'd been building a solution and you looked at magnetic and thought that wasn't the right one for my database, I should probably go and use provisioned IOPS, so you created a provisioned IOPS volume, maybe a terabyte. Once you've created that volume, you're working on it, it's no problem at all. GP2 launches, so now you have a system where you have an option to maybe use a different volume type. What would that mean for the environment? What I want to highlight here is that if we were to go from a 4,000 IOPS volume to just a 3,000 IOPS 1 terabyte volume with GP2, we'd substantially reduce our cost. And now, what I would typically be doing here is looking at something like a test dev database. It's not likely our production database we're going to move on to GP2. That's what provisioned IOPS is targeted for. But if it's a dev test environment, GP2 is probably a good fit for this, and it's going to substantially reduce our cost. You could also, if you wanted to be a little creative, and this is one of the capabilities you always have, is to build the volume configuration how you want. You could take two 500 gigabyte volumes. Each volume has a burst bucket of 3,000. So now our baseline performance would be 3,000 IOPS, and our burst bucket would be 6,000. So we'd actually be able to burst in IOPS much higher than we would have been able to use with provisioned IOPS, because provision gives us exactly what we're looking for. So we would actually get a boost in performance for our dev test database. So some guidelines for sizing. How should you go about sizing, or how should you go about building and setting up GP2 volumes? So for generic boot volumes, developer volumes, or just data volumes that you want to attach to instances, provision the number of gigabytes your application requires. We don't expect, and I hope you don't have to, over-provision a volume. You should just be creating the size of volume you want. And I'll talk a little bit around how you can move and migrate from volumes so you can easily get to another volume if you want. For database apps, typically you want to calculate what you think the baseline IOPS for your application is. Probably easier said than done, but worth the effort, I think. If you calculate the baseline IOPS, you then should be able to take those IOPS, divide by 3, and it should tell you roughly the number of gigabytes you want to provision for that volume. The beauty of GP2 for a database application like this is it's going to handle things like rebuilding indexes, loading tables with the burst bucket. So you're not going to be sizing the volume for the peak load, you're going to be sizing the volume for your baseline, so your steady state on that database. So digging into our second volume type is provisioned IOPS. Provisioned IOPS, or PIOPS as we tend to call it internally, is really focused at tier 1 databases, mission critical applications. Applications where you have a certain level of performance you need to be able to deliver in your application, and you want to know exactly what that performance will be and have a certain level of consistency that goes with it. So you can go up to 20,000 IOPS on a provisioned IOPS volume, so that's twice the number of IOPS you can do with an EBS GP2. The throughput is also twice, so it goes up to 320 megabytes a second, so it's a very substantial amount of throughput. Again, the latency, because all of our volumes, the GP2 and PIOPS are SSD backed, single-digit millisecond latency. Performance consistency is 3 nines of performance consistency. So 3 nines is what we're attempting to deliver of the IOPS consistency. And we target, like I said, mission-critical workloads with this. This is, when you think about having a database architecture, and you go to do a select on the table, and if it stalls for any moment at all, and that's not acceptable to your architecture, provisioned IOPS is the volume type that you should be looking at for that. A little bit of how we understand or how you can size the volume. So obviously volumes go up to 16 terabytes, both for GP2 and also for provisioned IOPS. Again, I don't believe this is to scale, so an EBS engineer will be confused by we don't do it to scale. But what you can do here is, with a very small amount of storage, go to a huge amount of IOPS. So one of the big fundamental differences between GP2 and provisioned IOPS is the ratio of IOPS to gigabytes. So in GP2, it was 3 IOPS per gigabyte. On provisioned IOPS, it's 30 IOPS per gigabyte. So you can see here that easily within, I think it's 677, if I remember off the top of my head, you'll be able to provision 20,000 IOPS into a volume. So it's very easy to have a lot of performance in a small amount of storage space. Last but by no means least, EBS magnetic volumes. So EBS magnetic volumes are typically used for data that's infrequently accessed. If you have a need to have something that's online, so you have a system where it must have data on a file system, you can't archive it off because no one's willing to agree to the archive changes in the application, but you need to have it online, we typically think magnetic is a great fit for this. So it's a lot cheaper because if you're not using it, it's only 5 cents per gigabyte per month today. And so it's a very low-cost solution to making sure you have online data access. Slightly different performance characteristics than our SSD-based volumes. So about 40 to 90 megabytes a second, and the latency varies for read and writes based on the media type. So a bit of a summary of all the different volumes and the capabilities. These are obligatory slides so that everyone can get a picture of them and take them home. Everything goes on SlideShare, folks. You can get it afterwards. The big things I'd like to call out here is the fact that the latency for SSD-based volumes is consistent. So it's designed for single-digit millisecond latency, 1 to 2 milliseconds. Our general purpose volumes are very, very easy to price and very easy to understand. It's 10 cents per gigabyte per month. And all of our GP2, or all of our SSD volumes go up to 16 terabytes now. So why have we made general purpose SSD the default? Well, why did we do that? And so if you haven't noticed, or if you're a new user on the platform and you grab an EC2 instance and try and launch an AMI that has magnetic as the boot volume, we actually pop a little dialog up on the console and say, hey, we notice you're not using GP2. Would you like to make this the default? And we've worked very hard to make GP2 the default on all of the Amazon Linux AMIs and worked very hard with the Windows team to get Windows as using GP2. The high baseline level of performance is the first aspect. So we can deliver a really high level of baseline performance for our customers in that environment at a consistent cost. The bursting capability we think is very important. It enables your applications to not be bound by a baseline of performance and get a lot more capability out of it. The single capacity-based pricing dimension, so the ability for you to no longer have to calculate how many IOPS am I going to be doing versus how long is the volume going to be created. And we've managed to, in our opinion, get an attractive price, gigabyte price, IOPS density ratio. So a little bit of a takeaway here. Always use GPU or general purpose SSD volumes or volumes for boot. If you have AMIs that you've built up, if you're a longer term user on AWS and you have a catalog of AMIs which are designed for all the different application stacks that you run, you should take a moment and check to see whether those AMIs are actually using GP2 by default on those volumes. If it's in an auto-scaling group, you can just change the block device mapping. You don't need to go in and change the AMI specifically. But if it's an AMI and it's EBS backed, it's very easy to re-register that. Just take the same snapshot and re-register, choosing GP2 this time to launch it. So how do you migrate onto GP2 volumes? How do you get onto general purpose volumes? So you can change the volume type at launch. So if you're launching something and you want to use a different type of volume the next time, you can just change that at launch. You can use EBS snapshots to easily get from one volume type to another. And it's not just to GP2. You can go from provisioned IOPS to GP2 or magnetic to GP2. It's very easy to do that. So when you create an EBS snapshot, the EBS snapshot doesn't have any relationship with the volume type underneath. So you can then take that snapshot and create a new volume with the new volume type that you want to use. You might be able to resize your file system. So if you've over-provisioned in the past, maybe you had a volume that was larger because you felt that that would give you the performance you were looking for, you might be able to resize that when you go to a new volume type. And when you're trying to work out what sizes you're looking at, use our general purpose sizing guide. So snapshots. Snapshots are really important. Snapshots are an aspect of the platform that enable you to introduce the concept of backups to your volumes, but also introduce the concepts of disaster recovery by having volume data in another region, or easily sharing volume data through the form of a snapshot with other accounts or other teams. So you can have a dev test environment, and once you're done, you can take a snapshot from that dev test environment, share it with the production team, and they can use that to move into their environment. So they're more durable than an EBS volume, and that's because they're stored in Amazon S3. So that's 11 nines of durability. And I'm going to talk a little bit around what happens. How do we make a snapshot so you can get a feel for what we're doing. They're incremental, meaning they're space efficient. So the first snapshot is a copy or a clone of the whole volume. And so we copy that volume as is. And then you only pay for what you actually use in snapshots. So if you create a second snapshot, so you created a first snapshot on, say, a 100 gigabyte volume, and then you change 5 gigabytes of data on that volume and create a second snapshot, we only snapshot 5 gigabytes of data. So it's very, very efficient to make your snapshots and also very, very cost effective. They're completely independent of availability zones. So they live in the EBS snapshot service, so it's part of the EBS service overall, and they can be recreated as volumes in any AZ or any region. And they can be copied across regions. So I wanted to take a moment and explain what happens when we make an EBS snapshot. It's not really black magic. It's just worthwhile understanding how we do this. So an EBS volume, because block storage is made up of blocks, okay? Only blocks written to are marked as updated. So we keep track of a volume and we go, hey, you wrote to this block, you wrote to this block. We keep track of that. That's part of the EBS service. That enables us to also not back up blocks that haven't been written to. At the point of snapshot, we make a list of all of the blocks to copy to S3 or to back up to S3. That's the first thing we do. Then we copy the snapshot blocks up to S3. The minute we've made a list of the blocks that we want to copy, that's when the API returns and says snapshot creating. At that point, you can start using your application again. There is no need to wait for a snapshot to complete. We've already tracked exactly what blocks we need to copy back up to S3 to make the snapshot. So that means that you can do snapshots in a matter of seconds. You can QSC your volume if required, call the EC2 create snapshot call, and when that snapshot comes back as the API call returns and the status will be creating, that's it. You don't need to wait for it to be completed. And I wanted to highlight that because I've actually come across customers who were concerned that they had to wait for the completed status before the volume snapshot was actually ready to move forward. And so when you create a future snapshot, we just keep track of the blocks that have been updated since the last snapshot. And so that's the magic part of it. We always know at what point blocks were updated and whether they were updated before or after the last snapshot. And then we only copy those blocks up into S3. So the tagging of snapshots. Tagging, please tag, tag, tag. So snapshots are even worse if you don't tag them, because then they're just sitting there and you don't notice them at all because they don't turn up in your volume list for attaching. So snapshots should be tagged as much as possible with data that will help you do management of snapshots. So we give you some examples here. You can choose any snapshot tag you want, and it can be irrelevant to your application rather than what we're suggesting. Some of them will actually automatically happen. So volume ID, I believe, automatically appears as a tag in there. So we keep track of what volume it came from, so you can do that. But you should track things like whether they're daily or weeklies, or whether they belong to a particular application stack, it's the web stack or the database component. And definitely want to tag as much as possible, because once you've done tagging, you can go into the AWS console. And if you haven't noticed, the AWS console has got a really improved search capability now, where you can start typing in tags, you can do ands and ors and build up a whole list. So you can do snapshots of tag application web stack, type daily, and it will bring back all of those snapshots. So a couple of tools I want to recommend. So customers, we talk to our customers as much as possible, and these are the two tools that I thought sort of stood out the most of tools that customers are using to manage snapshots. And these are tools they're using to manage the making of a snapshot on a schedule, so Schedly. And then also EC2 Consistent Snapshot. It's a GitHub project or an open source project someone wrote to do QSing of a volume. And so when you want to make database snapshots, you truly want to make sure that the volume is got all of the I/O written down before you make the snapshot. These tools just make it substantially easier for you to make snapshots. They're going to add tags appropriately if that's one of the things they do. And they're going to enable you to do things like schedule a snapshot to happen every day or every week. So a little bit more about EBS optimized, or a little bit about EBS optimized instances. So everything I've covered so far is about the EBS volumes, about the EBS snapshots. But because we run inside EC2, there's some properties of EC2 which are quite important to understand as well. And so an EBS optimized instance is an instance that has dedicated network bandwidth allocated to EBS traffic. So because it's network block storage, we have a network component between us and the EBS servers from an EC2 perspective. And with EBS optimized, you're able to get a dedicated amount of bandwidth allocated to your instance, so that if you've got a heavy application stack you're running, the traffic to the application stack is not contending for data on the EBS traffic. Our instances, things like the 8 extra large instances, actually support all the way up to 10 gigabits per second of network traffic. And there's a maximum number of IOPS and throughput on each instance. And so this number is much larger than what you can do with a single volume, but when you start to put lots more volumes on there, you find that the instance itself has got some challenges. And I'll make a shout out to the next session on the performance. We'll talk a little bit more in that session around how to understand whether it's your instance which is the bottleneck, or if it's the volume which is maxed out on the throughput. So EBS encryption. So EBS encryption is a great addition to the EBS service. It's for most customers the ability to tick a box and have volumes encrypted so they can then move forward without having to worry about how it's done and what happens to the volumes. So why are customers encrypting data volumes? Some of the primary reasons we see is protection of data, so protecting against unauthorized access of a physical volume. It can also help with your compliance efforts. So you may have some workloads that require encrypted data, and it's very easy to use EBS encryption for that. Why we're seeing customers move towards EBS-based encryption is ease of use and the operating cost reductions. So there's plenty of open source tools. You can use things like encrypt and build your own encryption on top of it, or third-party tools like Trend Micro. But they typically come from an open source perspective with quite a lot of operational overhead. You don't want to be building your own key management infrastructure or dealing with key rotation in that. And in the third-party aspect, it can add an additional layer of cost that might be prohibitive for certain applications. So how does EBS encryption work? So the first thing is EBS encryption is sort of mated with or paired with the AWS Key Management Service. So it's a managed service that simplifies creation, control, rotation of encryption keys in your applications. And when we say in your applications, that means your own applications, or you can have KMS provide keys to other parts of the AWS services, such as EBS. So it's integrated with AWS server-side encryption, and EBS should be listed. Yeah, there's a second in there. Server-side encryption means that the data is being encrypted on the server side, so not on the client side when you're connecting to it. Although there's one really unique capability of EBS I want to highlight here, and I probably should have a slide so we can dive into it a little bit deeper, but EBS encryption occurs on the EC2 host. So if we think a little bit around how the architecture of the environment looks, We have an EC2 instance that runs on an EC2 host, and then we have an EBS volume, which is exposed to the EC2 instance, and it's coming from the EBS service, which is sitting somewhere else inside AWS, separate from the EC2 instance. That encryption occurs at the host level. What that means is that encrypted data goes all the way across the network, and it's in the volume as well. So we have encryption on the wire and encryption at rest with AWS encryption there. It's also integrated with our client-side encryption, so folks who want to dive deeper into the encryption, you can integrate it with the SDKs or with the Dynamo client. And it's integrated with CloudTrail, and this is very important for people who are working on compliance. So CloudTrail is going to track all of the use of the KMS APIs. So when people are accessing a volume, or people are creating a key, or people are sharing a key with another part of the application stack so people can access the data, this is being logged in CloudTrail so that you can keep track of who's used it and where. And it's available in all commercial regions except China today. So a little bit about encryption keys and how they relate to EBS. And so you should be able to see in here that the second key from the bottom is AWS EBS, and it's got the little orange or yellow AWS icon beside it. What this is what we would refer to as the default customer master key. And so there's also in here a couple of other keys, highly confidential, critical data. So when you create keys, you can have keys for your own application stack, and then you can use them. Or services that support KMS will automatically create what we call a default customer master key. Now with a default customer master key, this is typically for people who just need encryption and they're not too worried about where the keys are going to be managed and what's going to be the policies around those keys. A default customer master key is only in your account. It's only accessible for your resources, but you don't need to specifically select the key name when you're going to do encryption. So I'll give you an example here of how easy it is to encrypt with EBS. If you're going to be launching a new volume or creating a new volume, there's a checkbox, encrypt volume. So once you've checked that, you're ready to go. And then you can choose a key. And so in this example, we're actually using the critical data key. Now what this means is that key is going to be associated with that volume and also any future snapshots. So snapshots are going to be encrypted by default because it's a copy of the volume data and the volume is encrypted. And then we can actually do custom things like key rotation on this, and we can manage what instances or what users or what groups have access to the critical data key, and that will actually control who has access to that volume within your environment. So a little bit of summary of what we've covered in the session so far. So start out with selecting the right volumes for your workloads, okay? I think it's really important to understand we have 3 volume types. We think GP2 is the default for almost all applications. If you've got a mission-critical workload, tier 1 database, an application that's very, very dependent on consistent I/O, it's provisioned IOPS. And magnetic is still a really good choice for volumes that are infrequently accessed or data that's infrequently accessed. Select the right instance for your workload. So when I mentioned EBS optimized, make sure you're choosing the right instance. Something I didn't touch upon, which I'll dive into a little bit, is if you grab a 2 terabyte provisioned IOPS volume with 20,000 IOPS on it, and you attach it to a T2 micro, it will not do 20,000 IOPS, and it will not do 320 megabytes a second. The T2 micro instance is a very, very small instance. It's a micro instance. And so it's sized appropriately, and the resources of that instance means it can't drive a really large volume like that. Take snapshots. Take snapshots as often and as much as you can. That would be really great. And then use encryption if needed. It's very, very easy. It's a checkbox. You tick it, encryption turned on, and you're ready to go. And with that, I'd like to thank you very much for our overview of EBS, our deep dive in EBS.